Hi everyone, in this video we are going to talk about how we can compare boiling points and melting points of different compounds. Alright, so in your head there should be a mental map with all the different factors affecting the different boiling points and melting points. So I'm going to share with you a very quick summary of the two different types of questions that you need to know how to answer. So first and foremost, the first thing that you need to do is to figure out the structure of the different molecules. The structure of your different compounds. Right. So first and foremost, you will need to determine the structure of your various compounds, right, or elements. So for example, if I were to give you this AlCl3 versus Al2O3, right, this is an example that you need to know really well. We know that this is giant ionic in nature, and AlCl3 is simple molecular in nature. Right, so this is something important that we need to do first, right? So which brings us to the second point, which is our bonding. So what kind of bonds hold them together, and what kind of bonds are we breaking over here? Right, and hence, using that, we can talk about the properties. Are we talking about the boiling point or the melting point? All right, which is the breaking of the bonds itself. So the first type of questions that you'll see is that where we compare between giants and simple molecular structures, where in this case, the giant ionic structure, right, will definitely contain stronger ionic bonds than any of these simple molecular structures. Right? And that is the reason why whenever we compare giants versus simple molecular, we just need to say that the ionic bonds or the covalent bonds or the metallic bonds are stronger than the intermolecular forces of attraction in simple molecular structures. So this is quite clear-cut, giants versus simple. Right. However, you can also have questions where you are supposed to compare within the structure. So I will have four different structures here. I have ionic, right, I have covalent, all right, giant covalent, we have giant metallic, and then finally our last structure is we have simple covalent. So for our giant ionic compounds, we simply have to use the lattice energy equation, right, to study it. So do take out the lattice energy equation. You'll realize that it's proportional to Q plus times Q minus over R plus plus R minus. So please use the lattice energy equation and not charge density. They have very different equations. Next, if we look at the covalent bond strength, if you are breaking bonds, for example, in SiO2 or carbon in terms of graphite or diamond, right, we have to look at four different factors, right? The effectiveness of the overlap, we have to look at the bond order, we have to look at S character, and we also need to look at ionic character. Right, so this is something that you can figure out from your own set of notes. And for the metallic compounds, right, the way to look at it is you simply have to look at the charge density of the cation. So it's Q over R, the charge over the radius, and the number of delocalizable electrons. Right, so the number of valence electrons that are delocalized, right, will affect, right, this sea of delocalized electrons and hence the metallic bonding. Finally, for our simple covalent structures, you need to know whether it is ID-ID interactions, whether it's PD-PD, whether it's hydrogen bonded. Right, so that's the first step that you should take. Right, but sometimes, right, some ID-ID interactions are indeed stronger than that of hydrogen bonds, right, and that is caused by the number of electrons. So you can compare between ID-ID and ID-ID, or compare ID-ID with PD-PD or ID-ID hydrogen bonds, permutate them differently, right, and look at the various factors within them. So for ID-ID interactions, there are two factors, namely the surface area of interactions and the total number of electrons. For PD-PD is simply the net dipole, alright, whichever molecule has a greater net dipole will have a stronger PD-PD interaction. And lastly, for hydrogen bonding, it can be the average number of hydrogen bonds or simply the polarity of the XH bond, where X is equal to F, O, or N. So do take note of that. Alright, so in summary, right, this video is not here to tell you all the different factors only. Alright, so you can refer to that from your own lecture notes or school notes. But what is important is to understand that when we compare boiling points and melting points, we're essentially comparing between giants and simple, or we can compare within the structures itself, ionic compound versus ionic compound, covalent versus covalent, metallic versus metallic. All the simple molecular structures, you need to know whether it's ID-ID, PD-PD, or hydrogen bonds, compare between them. But do take note that the assumption is that the number of electrons are comparable. If they are not, you have to look at the data to determine whether ID-ID is stronger than that of hydrogen bonding if there's a lot more electrons in play. Alright, so essentially, this is how we can use structure, bonding, and then properties to explain the comparison of boiling points and melting points. And one last note before I end this video is that for melting point, it also depends on how the particles are packed together. So sometimes the trend will be slightly different from that of the boiling point. So do take note of that. And with that, that is the end of this video.